Hey, everybody, and welcome to today's edition of the Spectral Geometry in the Clouds seminar. Today, we have the pleasure of hosting Jaume de Dios Pont from ETH Zurich, who will tell us about convex sets that can have interior hotspots. As usual, if you have questions during the talk, please either unmute yourself or ask them in the chat, and we'll relay them to the speaker. Jaume, the floor is yours.
Thank you, and thank you so much for inviting me to speak. I want to talk about a cute old question. Historically, comes maybe more from like spectral theory, mathematical physics, but it's not the take we're going to look at today. But let's start with that. Let's start by looking at the historical physics interpretation of all. You have a convex set, a body, a three-dimensional, imagine like homogeneous piece of material in space. And assume that it's a material with non-uniform temperature, but uniform composition. And also assume that it's well insulated from its environment in the sense that it doesn't transmit any sort of heat at the boundary with its environment. And you let it evolve. What's going to happen as you evolve, the temperature of this material is going to average out, it's going to become closer and closer to the average temperature of the material. Like things, when you let them evolve, they go into thermal equilibrium. The question that Rauch asked us was, which is the point in this material, in some sense, that takes the longest to reach this average temperature? How do we measure this? Well, I evolve my material for time t, and for fixed very large t, I'm going to look at which is the point that has the largest temperature, or like the largest temperature fluctuation around my average temperature. Let's see an example. This is a somewhat generic domain, and it has a definitely generic initial temperature distribution. What happens when we evolve this distribution over time? Well, it becomes more and more smooth, it becomes closer and closer to the average, and the hottest and coldest points are somewhere in the boundary. We don't know where, but maybe like the bottom left point and the top right point are the hottest and coldest points in our material. That's essentially what Rauch conjecture. That if I have a well-insulated, uniform bounded object, so yeah, like a reasonable like body from a physicist perspective, and I start with generic initial conditions, this is actually going to be very important, then for large enough times, the points that are like the hottest and the coldest, so the ones that fluctuate the most from this average equilibrium temperature, are going to be getting closer and closer to the boundary, or maybe actually be at the boundary for time large enough. Now, if we look at the temperature itself, it's kind of hard to see, it's kind of hard to understand, because everything is converging to this average temperature. But what I can do is I can sample a new generic initial condition, and instead of looking at U, at the temperature UT, I'm going to be looking at UT minus its average divided by its L-infinity norm. Or in other words, I'm going to be plotting the renormalized temperature distribution. So this is actually like zooming into the fluctuations of the temperature and seeing which are the points that have the highest fluctuations as t goes to infinity. An object like this acts like this. So now the situation is a little bit more extreme than before. And what we see is that these temperature fluctuations, in some sense, seem to be converging to a limiting object. And not only they converge to a limiting object, but this limiting object is to be like hottest and coldest, like at the points which are like furthest away from the bulk of the material. We're furthest away from the bulk of the material at this point is an ill-defined concept that we can get to, but like morally it means this furthest away should be points right at the bound. Now, why did I talk about generic? The thing is that we know that the conjecture is false for very non-generic initial conditions, very non-generic objects for symmetry reasons. So here I have two different possibilities of initial conditions. The one on the left is as far from generic as possible. It's radially symmetric on a ball. The one on the right is very much generic. It's the same one, but I've perturbed it a little bit, so it looks generic. So let's see what happens on the object of the left. Well, it starts radially symmetric, so it has to stay radially symmetric forever. The temperature converges to the average temperature, but the fluctuations look like this. Again, I'm always plotting the fluctuations around the average temperature, which I'm just renormalizing as I'm doing my simulation. What happens in the object of the right? Well, as soon as I'm ever so slightly off of this generic initial condition, something very different happens. There's some symmetry breaking, and this just off the radially symmetric situation becomes very extreme very fast, and you converge to something that has one preferred direction, hot to cold, and the hottest and coldest points are at the bound. But we needed the genericity. In the non-generic case, we already knew that the conjecture. Now, pictures are cool, but let's try to do some mathematics around it. So we've hopefully all seen the heat equation at some point. The heat equation tells me that the derivative of the temperature, which I'm denoting by U, is the Laplacian, or maybe proportional if you want to add the physical constant, to the Laplacian of U. This, in other words, is telling me that the temperature at a point is getting closer to the average of the temperatures of my neighbor. That's what the Laplace operator does. And we also know from a physical point of view that the temperature goes from hottest points to coldest points. The heat flows from hottest to coldest point, and it flows in the direction of the gradient. So insulating boundary conditions means that this heat flow, that this flow of energy cannot go through the boundary. In other words, that the gradient of U has to be tangent to the boundary, cannot have any normal component, or in other words, that the normal component is 0. This is what we call Neumann boundary condition. And then whichever boundary condition you start. Okay, how do we solve such a problem? Well, there's the brute force approach, which is diagonalization. So we know that this Laplace operator in omega is, at least the minus Laplace, is a non-negative definite operator with first eigenfunction, the constant eigenfunction, and can be diagonalized. So there exist a bunch of functions, the phi omega j's, which are the Neumann eigenfunctions with Neumann eigenvalue of my operator. And we also know that these eigenfunctions are a basis of my my space, say of L2. Since these eigenfunctions are a basis of L2, I can write my U of x0 as an eigenbasis expansion. So I can write U of x naught as the dot product expansion. And eigenfunctions are great because I can solve the heat equation for Laplace eigenfunctions because of the product answer. It's basically a Laplace eigenfunction stays an eigenfunction forever, and you gain an e to the minus lambda t like this. So this is a solution. This is a linear combination of solutions. So it's a solution. So it gives me the solution of the heat equation. And this also, once we have this, we understand why genericity. So if this is the solution, we see that at infinity, the main dominating term is the average. And after the average, we get this series of exponentially decaying terms. Which is the term that's going to dominate once I remove the average and I go to infinity? Well, the first one that is non-zero. The lambdas grow, so as t goes to infinity, these things become smaller and smaller, and the one that is the least small is the one that's going to dominate. Generically, the one that's going to dominate is the first one, because if I start with a generic initial condition, it will not be perpendicular to the first eigenfunction. This explains what was happening in the symmetry world, in the generic versus non-generic. In the non-generic example, we were actually orthogonal to the first one, and we didn't see it. So we converged to the third one, which is the first one we were not orthogonal to. Now, this explains also why there's these limits that we saw in the first picture. As I look at the fluctuations, they converge to something, and they should converge to this phi 1 omega. And this lets us refine the Rauch conjecture and see the conjecture that he actually posed. So the conjecture that he posed was that for all nice sets omega, the maximum and the minimum of this phi 1 omega are attained in the boundary. Again, asymptotically, this is the same as telling me that for generic initial conditions, the maximum and the minimum are attained. And this is what Rauch actually proposed to us in '74. And it's a really beautiful conjecture, kind of reasonable from a physics perspective. And so a lot of people have looked at it. And what have we learned through it? So what do we know? We know that it's true over the reals. Why? Well, I mean, there's only up to dilations and translations, which are not physically relevant. There's only one bounded set, which is the interval. For the interval, the first Laplace eigenfunction looks like a sine. A sine that goes from -1 to 1, -1 on one end, +1 on the other end. The maximum and the minimum are at the bound. We also know in R2 that the conjecture holds in certain situations. For example, for triangles. Triangles may seem easy, they're extremely hard. The proof is beautiful, but extremely delicate. So it's kind of a hard problem to prove things in the positive. We also know it for convex sets that have two axes of symmetry. We also know it for sets that are in the domain between two one-Lipschitz functions. So xy such that y is between f of x and g of x, where f and g are Lipschitz functions. Then you build like a one Lipschitz domain like this. We also know things about RD. For example, a classical thing is if omega is some sort of cylinder set or product set. So you take an omega, you take a product times an interval, and then you can use these symmetry considerations. It's easy to construct eigenfunctions of the product. They're basically products of eigenfunctions, and you play with it. Then there's certain really nice new generalizations of one Lipschitz functions to higher dimensions. A very nice, very new result by Kennedy and Rochelder, where they find a very large class of higher dimensional sets where it holds. And then there's this result, which about this constant, which was originally posed by Steinerberger, which is, well, maybe I can't prove the conjecture, but I can define like a relaxation of the conjecture. Maybe the maximum is not right at the boundary, it's inside, but how bad can it be? So he defines this constant, Steinerberger defines this constant, which is the supremum of your eigenfunction inside divided by the supremum of the eigenfunction at the boundary. You expect this to be at most 1 if the conjecture holds. If the conjecture holds, the maximum at the boundary is as big as the maximum in the interior, so this is 1. But then Steinerberger posed this. Actually, I think there's a like Mariano Panzo and Wang improved this, and the 6 is not by Steinerberger, it's by Mariano Panzo and Wang. But essentially, there's this constant which is bounded, and most importantly, it's bounded independent of the dimension, independent of everything. So, I mean, there's at the very least some truth to the conjecture. And then there's another result, which is also by Steinerberger. Here, Mariano Panzo and Wang. This is wrong. They should be up here. Which is that for thin convex sets, a thin convex set, you have to imagine like some sort of spaghetti type situation. The hotspots are at the tips, where the tips are like the tips of the spaghetti type object. He doesn't show that they're like right at the boundary, but he shows that they're very, very close to the boundary. And today, the goal of today's talk is going to be to like generalize these to higher dimensions and fail spectacularly in the process. Now, we also know that the conjecture is not always true. There's this example, which is already by Burdzy and Werner in 1999, which shows that sometimes the maximum is not at the boundary, at the expense of building topologically complicated domains. This has been improved later. We can build domains with one hole. We can build domains where both the maximum and the minimum are not at the boundary. But now we have just one example where the maximum is inside. So let's play the picture, the video, and see what happens. Essentially, what's happening is that I have two regions that are very poorly connected. And over time, one's going to be like the hot region, one's going to be the cold region. And well, which is the point in the hot region that's going to be the hottest? The one that's furthest away from the cold region, which is the one in the middle. So basically, by forcing this some sort of like almost radial symmetry, they're able to provide a counterexample. Their proof is not numerical. Their proof is like pen and paper. They actually have 3 holes instead of 4 holes. It's the minimum amount of holes that you get with this method. But more than anything else, that you get the idea that whether the conjecture is true or not is not a universal fact. Now, once we have this example, like there's a point where the mathematical community has to decide, like, what do we believe? How optimistic are we? Maybe you're extremely optimistic. This is, I've never seen this stated. I never saw this stated, but this is like the most optimistic thing you could ever say, which is that the holes are important. And therefore, in RD, any topologically simple domain will have hotspots at the boundary. Maybe you believe that topology is too weak of a statement, but convexity is important. As you've seen, we're able to prove a bunch of results for convex sets. maybe you believe that there's some sort of magic in dimension 2. This is not unwarranted. Topology is much more of a stronger statement in dimension 2 because we have complex analysis. Complex analysis sees topology very well. Laplace operator and complex analysis behave very well with each other. So maybe there's like some two-dimensional magic. And if you're like completely pessimistic, you believe that convex sets in dimension 2 or in very low dimension are true, and anything else is false. And you have to draw the line somewhere. Until very recently, this is where people would draw the line. And what I want to convince you today is that the natural place to draw the line is actually here, that this one is false. We're not going to see the whole proof today, but the goal is to convince you that this one is in fact not quite reasonable. And the way I'm going to try to convince you is by generalizing this result by Steinerberger, the one that told us that the hotspots were at the tips, and seeing that this is false. The way we're going to do it is as follows. So let's go to 3 dimensions. What is the 3-dimensional generalization of this like very long, very thin convex? There's a bunch of them depending on the size of the dimension. You could consider some sort of like pancake situation, some sort of spaghetti, again, 3-dimensional spaghetti, a plank. I'm going to be looking at the pancake situation. So when I have 2 dimensions that have like sort of size 1, and 1 dimension that is very, very thin, that has like size like 10 to the minus 10, I don't know. And you imagine like, what does the temperature look? Now, if you're a physicist, the very first thing you're tempted to do is forget about the small dimension and build a 2-dimensional effective problem. It's like, it's like a sheet of paper. It's a 2-dimensional object. I'm going to forget about the 3rd dimension, but maybe my body is not uniform in the 3rd dimension. It's like some sort of like full pancake. So I have to build an effective PDE in 2 dimensions that's capturing this behavior in 3 dimensions. And now this is a 2-dimensional object. So it has a 1-dimensional boundary. So suddenly what we're saying is that it makes sense for very thin 3-dimensional objects to talk about like a 1-dimensional ring around them. And that's what we're going to do. So we're going to define this version of the thin hotspots conjecture, copying Steinerberger, which is going to be like hotspots are at the ring. So if you have a very thin 3-dimensional object, then the hottest and the coldest point for a long time are not only going to be at the boundary, but they're going to be very close to like this rim. That's a 1-dimensional kind of boundary thing. How do we formalize this? Well, so that's going to be today's focus. It's going to be to look at this conjecture. So let omega be a set in D RD cross RK, where RD you have to think as the big dimensions, and RK you have to think of them as the tiny dimensions. And then where does this like effective lower dimensional PDE live? Well, in the big dimensions, I forget about the big ones. So I define P to be this like lower dimensional object. Now, what is a very thin pancake or a very thin plate? It's an object where I start with my original convex set, and I get the small dimensions, and I make them very small. I compress them by epsilon. So I start with a ball, and I squash it in 1 dimension, and I get a pancake. And the conjecture, if we want to follow Steinerberger, is that as I do this, the points, the maximum and the minimum of my eigenfunction should be moving closer and closer to the boundary of this lower dimensional object. This will be some sort of like robust version of the hotspots conjecture. And today, what we will actually see is that this conjecture is false, that at least for large dimension and large K, this stable version of the hotspots conjecture is false. Following the same argument, if you work very hard, you can actually show that the hotspot conjecture is false, but it requires quite a lot of work and pushing through the same argument again. Now, what would a counterexample to thin hotspots look like? So I've drawn something like this. This is different from the picture below. It's somewhere where the hottest and the coldest point, they could in principle still be at the boundary, but they're far from this like lower dimensional ring. So what we want to show is that there exists weird convex sets for which the Laplace eigenfunction looks something like this in a certain sense. They're not going to be in 3 dimensions. They're going to be in very high dimensions, but this is data. Now, before we do that, I want to talk a bit about convex analysis. And I want to talk about what happens when you make, when you try to play these games about forgetting of certain dimensions. This is a game that people in convex analysis have been playing for very many years. So we're just going to copy our tools. So in convex analysis, they define this so there's this object called the log-concave measure. a log-concave measure is a measure that has a density for us, such that the logarithm of the density is a concave measure, is a concave function. That's log-concave. In other words, saying that the logarithm is concave is the same as saying that my density can be written of the form e to the minus v, where v is convex and v is called the potential associated to this density. Now, my v is a convex function, but I allow it to take plus infinity value. Now we have two examples, which are, I think, the most important examples of log-concave measure. First one is a Gaussian. Why do we like this one? Well, x squared is the easiest convex function. So e to the minus x squared has to be the easiest log-concave function. And the second one is indicator function. If A is a convex set, I can build a potential that's like 0 inside and infinity outside. And using the convention that e to the minus infinity is 0, when it's like what happens when you take the limit, you get that indicator functions of convex sets are a particular case of log-concave measure. But there's this like leitmotif, this pattern that keeps on appearing in convex analysis, which is that if you have an inequality that holds for all dimensions, for convex sets, then for free, automatically, you can update it, you can upgrade it to log-concave measure. And morally, this is what we're going to say about hotspots. We have like this inequality version of hotspots by Stadner-Berger. And if the inequality was true for all convex sets, it should also be true for all log-concave measures. That's kind of the deal. And then we're going to see that it's not true for all log-concave measures. And I'm going to give you two examples. So the one in hotspot is particularly like, it's quite a bit subtle. So we're not going to talk about that one today, but I'm going to give two easy examples to motivate you. The first one is the Minkowski inequality, which if you haven't seen, I'm going to talk about, which implies the Prekop-Alleinler inequality, which is a generalization of the Minkowski inequality for log-concave measures. So I'm going to define both of them today, and I'm going to explain you how to go from one to the other, which is going to motivate what's like the key construction in the paper. And the second one had something a bit deeper, which is the KLS conjecture. Again, I'm going to introduce the KLS conjecture in a second, but there's two of them. There's one for convex sets and one for log-concave measures, and we're going to see that you can upgrade from one to the other for free. So let's talk about Minkowski and Prekop-Alleinler. So I'm going to present the dimension-free version of Minkowski. This may not be the one you're used to, but a cheap change of variables turns it into the one you're used to. So you start with two measurable sets in RD, and you have this inequality. Why is this inequality about convex sets? Because the equality case is when A and B are convex and equal or proportional to each other. So you start with this dimension-free type Minkowski inequality, and then you want to do something else, which is the Prekop-Alleinler inequality. In order to define the Prekop-Alleinler inequality, I have to define a bit of a scarier object. So given f and g, two functions that go from Rd to R union infinity, again, it's a bit easier if you pretend that these two functions are convex. Then I defined what I'm going to call like the convex extension of f and g to be this monster. You can look at the equation, you can stare at it for a while, but I think it's easier if we think about it from a geometric point of view. If f and g are convex, I have a function of two variables, z and lambda, such that when I put lambda equals to 0, I get g. When I put lambda equal to 1, I get f. And in the middle, I get the largest convex extension of f and g. So in other words, this is the convex interpolation between f and g. So the biggest convex thing that I can put between f and g. And in general, if f and g are not convex, it's sort of the same. It's like the biggest convex interpolation you could take from all of them. In particular, something that is cute is that if you take them to be indicators, then it gives you the indicator of the convex interpolation. And the Prekop-Alleinler inequality tells me something like the thing before. If I use this f and g, which it's easier if you pretend they're convex, to build log-concave measures, then I have this geometric mean type estimate, which is kind of remindful of the one above. Not only it kind of reminds us of the one above, if I restrict f and g to be indicator functions of my set, so like 0 inside the set and infinity outside, the Prekop-Alleinler inequality, this one over here, actually gives us back the Minkowski inequality. This is, at this point, it's just like algebra chasing. You put f and g to be the indicators, and you just like start chasing the definitions around your statements, and what you recover is exactly Blooming-Kofsky. This is what I'm going to call a cheap result, and I'm going to call it cheap. My difference between cheap and expensive is that for every fixed dimension, if I have been able to prove the Prokop-Lindler inequality, I recover the Blooming-Kofsky inequality in that fixed dimension. Now, it turns out that you can go the other way around, that you can start with Blooming-Kofsky and you can prove Prokop-Lindler. But this is an expensive result, and I'm going to tell you why. So I'm going to define these sets Fk, which I'm going to call barrel domains. And again, they have a very specific definition. Delta K doesn't matter to us right now, but let me draw them. So I give you a potential V, something like this. And then you use this V to trace a radially symmetric object. So this V, your potential V, you use it to build the shape of a barrel, of some sort of barrel. But it's not a barrel. So here I'm only adding 2 dimensions because I'm constrained by like knowing how to draw 3 dimensions. But in practice, you add a lot of dimensions as well in the radial direction. So you have a potential in the dimensions, and then you create a barrel in a lot more dimensions. And the more dimensions you add, the more your barrel looks like a cylinder. So it's like a V of x over k. So it's when I have a lot of dimensions, it's this object which looks like a tiny, tiny perturbation of a cylinder. Now, why do I like this object? So when I forget about the k dimensions, but you should think again as like the small dimensions, I recover a log-concave measure. Let me tell you what I mean by this. So if you look at, let's compute the volume. I think just the volume computation is very enlightening about what's happening. So if you compute the volume of this Fk, and just to make it make sense, you renormalize it by the volume of the ball. What happens? Well, these Fks are like some like graphical sets over Rd. So I can compute their volume by integrating over Rd. What do I have to integrate over Rd? I have to integrate over Rd the volume of the slice that I get in the other k variable. Well, in the other k variables, I get, and now I'm setting delta k equal to 1, just for simplicity. In the other variables, I get the radius to the k. The radius to the k is, well, the volume of the volume of the slice, then is the volume of the ball times the radius to the k. And now comes the piece of magic, which is you have this object over here, and you apply like the favorite like calculus 1 student limit, which is like 1 plus 1 over n to the n is equal to e, as you send n to infinity. So when we have these Fks and we compute the renormalized volume as k goes to infinity, we recover the integral of the log-concave measure associated to V. Now, if you do again the same thing, you diagram chase what's the convex combination of these Fks, and you just repeat the same arguments as before, you can show that Prokop-Lindler, that Blooming-Kofsky implies Prokop-Lindler, because you can simulate your log-concave measures associated to a potential by convex sets at the price of adding a lot more dimension. Now, this is not a cheap result because I need Blooming-Kofsky to hold for every dimension with the same constant in order to prove Prokop-Lindler in every dimension with the same constant. So somehow, like, to go like from the like particular case to the general case, I need all dimensions at the same. Okay. Now, since we were talking about Laplace operators, I have to define you what is the Laplacian for me for log-concave measure. So very often, instead of thinking of the Laplacian, it's easier as an operator, it's easier to think of it as a bilinear form. It's a bilinear form that takes 2 functions and computes the integral of grad f dot grad g. And when I think of it as a bilinear form and I want to compute the eigenvalues, I get the following variational formulation for the first eigenvalue. So the first eigenvalue is the minimizer of the bilinear form divided by the norm in the orthogonal of the trivial, of the kernel. The kernel, it's what I don't care about, and the kernel is the constant function. So it's functions that are orthogonal to the constant, functions that have mean 0. And I want to minimize over all of these functions the integral of grad f squared divided by f squared. This is lambda 1, and the minimizer is the first non-trivial eigenfunction. Now, this has a very easy generalization to the case of convex functions, of log-concave measures. What do I do? Well, there were a lot of very thin dimensions. I forget about the very thin dimensions. what happens then for log-concave measures? I can define the Laplace operator associated to that convex measure, to that log-concave measure, to be the minimizer of the same thing. But now instead of minimizing amongst functions of how do you call it? Functions like just the integral, I have a weighted integral that corresponds, if you want, in the picture below, before to all of the dimensions that we forgot. Now, integrating by parts shows you that this bilinear form, which is the one that we're going to get about, is associated to the following operator. This operator, the L omega v, which is the minus Laplacian as before, plus this grad v grad. So in other words, the minimizer of this optimization problem is going to be the first non-constant Neumann eigenfunction of this operator, omega v. Now that we know these two, let me give you an example where we apply all of these ideas. This is the KLS conjecture. So the original KLS conjecture tells us that there exists a universal constant such that if I want to look, so this is the optimization problem as before, which is the one that defines my lambda 1. And this is a very, very hard optimization problem because it's an infinite dimensional optimization problem. But what KLS tells me is that instead of studying this very complicated minimization problem, I can restrict myself to looking at affine functions whenever omega is convex. Now, how do I generalize this conjecture through log-concave measures? Well, trivial. For any log-concave measure, I should have the same. So now for every log-concave measure, I should have that I can approximate the spectral gap associated to the log-concave measure by the minimum over all affine. And to hopefully no one's surprised at this point, KLS implies the measure version of KLS. Not only that, very often in the literature, the only one you see people talking about is the measure valued version of KLS. Why is that? Well, it turns out that if V and grad V, this is not necessary, but like it makes the proofs a lot easier, are bounded in a certain omega, and then V is just plus infinity outside of this omega, then as you build these little barrel sets that I presented before, the limit of the first eigenvalues of the level sets converges to the eigenvalue of omega V. We're going to see an example of this later. We're like a little bit step by step. But basically, the whole idea is that I can simulate with my barrel domains this effective potential. And then corollary, if you can prove KLS for all dimensions with the same constant, you can prove KLS for all dimensions for log-concave measures as well. But you need KLS to hold with a constant in every dimension, which is something that we don't know how to do quite yet. What we know how to do is to show it up to a log. And as I said, this is an expensive result. So if you had it only for convex sets up to a log, you would have nothing about log-concave measures. Luckily, people are proving things straight away for the log-concave case. And yeah, this is like, we're almost there. There's been like a really, really great recent progress in showing KLS and showing that this constant is almost independent of the dimension. But the reason I presented KLS is because deep inside, KLS and hotspots are talking about the same thing. They're not exactly the same, but they're telling us a very similar story. So what KLS tells us is that I can pretend that my function, my first eigenfunction, is linear when I'm trying to do Rayleigh quotients in an L2 sense. So if I only want to measure things in L2, and I don't care about constant, I can just pretend that my first eigenfunction is linear. Now, hotspots, the thing that it tells me is that this phi 1 omega has a maximum that's attained in the boundary. But deep inside, what they're both telling me is that the gradient correlates very well with one direction. For KLS, well, if phi is essentially linear, then the gradient should be correlating very well with the direction where phi is almost linear. But that's in an L2 sense. For the convex hotspot, it's in an L infinity sense. Not only that, if you go back and look at most proofs of the hotspots conjecture for particular cases, what they're doing is they're finding one direction, which is the direction of growth, and showing that your function phi is monotonic increasing in this direction. Once you have that phi is increasing in a certain direction, you can show, I mean, you know that the maximum is at the boundary because you just continue flow. But today we're going to build an example where phi1 does not correlate very well with any direction. Okay, how are we going to do that? So let's introduce the hotspots conjecture for log-concave mesh. Let's go back and remember what was our big conjecture that we were going to discuss. So we have this extension of the hotspots conjecture, which is the thin hotspots conjecture, which is you take p epsilon to be like these very, very thin pancakes. And then there are like the maximum and the minimum are moving to the rim of them. If we follow everything that we did before very carefully, what we see is that knowing this thin hotspots conjecture for all amount of small dimensions implies a log-concave version of the conjecture. So you just take the domain to zero, like the thickness of the small dimensions to zero, and you recover the following stronger version of the conjecture, which is that every convex bounded domain and every, like, say, smooth potential should give rise to the hotspots property. So when I look at this phi VP, which was the minimizer of the weighted problem, I should still have the hotspots conjecture. So what we're going to see today is that for large D, at least, there exists a smooth potential VD such that this function attains its minimum and maximum only in the interior, so that this log-concave hotspots conjecture is false. Now, the rest of the talk is going to be running through this example. This example shares a bunch of ideas with the counterexample to the proper conjecture, but it's quite a lot easier to state, and it's like 15 minutes are enough to see to get the main ideas out. So let's pick our domains. Our domains are going to be of the form omega d, which is a very long cylinder, times in very high dimensions. So I have one dimension where I'm like big, like 200. This 200 is not important. It was just like for the precise constants that come in. And in the other direction, it has, say, a radius 10. And the potential, I'm going to build it so that it's radial in the second coordinate and bigger as d goes to infinity. Now, this basically the reason we're building it radial in the second coordinate is because we want to see pictures. The only way to see pictures is that this is actually secretly a two-dimensional problem. For this to be a two-dimensional problem, what we will need is that the first eigenfunction is radial in the second coordinate. So we're building like a radial potential, hoping for a radial eigenfunction. So lemma. This function is radial in the second variable. And not only is it radial, but when I look at it, when I look at the radial version, it solves another eigenvalue problem. So I can write it in polar coordinates, and I have an effective potential, which is the original potential minus log of the radial variable. And the rectangle, the new domain, is just like the cylindrical coordinates of the previous. So I have this domain, which is like one interval across a very high dimensional ball, and I can do a polar change of coordinates to get a rectangle domain. And the only thing this does is it changes my domain. So in other words, I want to show you that at least in very high dimensions, there's an example that looks like this. So there's a hottest point right in the middle and a coldest point right in the middle. And then I write it in polar coordinates. In polar coordinates, what I'm looking for is a picture like this. So the vertical coordinate is the radius. So I want to show that the hottest point and the coldest point are equals to 0. In other words, that these functions over here have the maximum right at the bottom. So the rest of the slide is going to be about building a U, which is nice, such that when I look at this other problem, the maximum and the minimum are right at the bottom. Okay, now prove that we have this decomposition. For a second, and I'm going to ask you, I'm going to borrow something from you. I'm going to pretend that we already knew that this eigenfunction was radial. And I'm going to show you that if it was radial, it would solve the effective problem. And then we're going to see that it's radial. So then if it was radial, I could use the minimization problem. And in the minimization problem that I have, which is like this gradient squared, I could integrate out over the balls. And I just turn it into a polar coordinate integral. And when I turn it into a polar coordinate integral, I get a Jacobian. What is the Jacobian that I get? The radius, which I'm calling y, to the d minus 1. So if phi twiddle was linear, well, was radial, it would minimize this. Now it's just algebra. You rewrite this extra term that you got, and you throw it inside of the exponential so that you have an extra weight. And now that explains also why I needed my potentials to be bigger and bigger as I add more and more dimensions. So yeah, at this point, we have a new problem where I have like bigger and bigger potentials, but I am in a fixed domain, which is the polar coordinate. Okay, now I've told you that if phi is radial, it will solve this. Now let's see that it's. So the thing about eigenvalue problems and spectral theory in general, when you compare it, say, to like general PDE, is that it has very rigid symmetry properties. Let's say that you give me an eigenfunction of the cylinder with this potential. Then what I can do is I can average it out to obtain an eigenfunction that is radial. So I can just average out over all possible rotation. This rotate like a rotation of an eigenfunction, if my potential is radial, is going to be a new eigenfunction. So I can average it out over all possible rotation. Doing that can result in two possible outcomes. Either it will give me a radial eigenfunction, or it will give me a mean zero eigenfunction. In other words, what that actually tells you is that you can decompose your whole eigenspace into radial eigenfunctions and mean zero eigenfunctions. By mean zero, I mean that they have mean zero over all possible spheres. So I can assume that my eigenfunction has one of those two properties. Now, if I want to show you that it's radial, I just have to show you that it doesn't have mean zero. So we can prove it by contradiction. So let's pretend that it had mean zero. If it had mean zero, if this function had mean zero over all possible spheres, then I could apply the Poincare constant of the sphere, or the maximum of the Poincare constants of the spheres, to get an inequality like this. The thing is that the Poincare constant of the sphere of dimension d is actually tiny. It's like 1 over d minus 1. Then I get the 100 out with the like homogeneity 2 of the Poincare constant, and I get a bound like this. I get that I can bound, if I was in the mean zero situation, I could bound the L2 norm of phi by 100 over d times the L2 norm of the gradient. Now, remember, what is the value of this lambda omega d? It's the quotient of the right-hand side of this graph phi squared divided by the norm. What this would be telling me is that the lowest eigenvalue is at least d minus 1 over 100. If, how do you call it? If the first eigenfunction is radial. But we're going to build the potentials. We haven't built the potential yet, so I cannot tell you anything about this guy. But again, I'm just going to like shove things to the future. I'm going to build the potentials so that these first eigenvalues at most pi squared over 4. Since d goes to infinity, if d is more than 500, then this is a problem. Something that I want to say here, and this is very important in the actual proof of the hotspot conjecture, or in the actual counterexample of the hotspot conjecture, is that we were very wasteful. If I had picked balls, say, of a radius comparable to square root of d, so square root of d over 10 in this example, I would still have gotten to a contradiction. So here I'm actually like in this inequality, I'm throwing away a lot of it. But if you want to actually do the proof without like log-concave measures, you don't get to throw away all of this work, and you have to be like a lot more fine, a lot more careful. Now, let's go and build the potential. So I'm going to build a potential, and in order to build this potential, I built it like literally by like playing with mathematics until I found an example that I liked. But I'm just going to tell you a laundry list of things that I want. So the first thing that I want is that the minimum of my potential is only taken in this tiny strip, which is the minus 1, 1 in the x variable cross 2 in the second variable. So this is where the minimum of my potential is taken. The minimum cannot be close to the boundary because it blows up. I have the minus log, but I can sort of set it a bit far from the boundary wherever I want, and I want it here. And what this implies is that when I look at the probability measures associated to e to the minus du twiddle, which are the probability measures that I care about, if I build my potential in a little bit of a nice way, these measures will converge to the uniform measure of this slide. Why is this? Well, this U-twiddle is big outside of the of this little slit, and let's say 0 in the slit. Then when I do like e to the minus this goes to 0 outside of here, and it stays 1 here. So eventually most of the mass will concentrate near this tiny slit. And if you construct things carefully, you can make these measures converge to the uniform measure in this slit. This is enough to show that the limb sup of the lambda omega v is at most pi squared over 2. Okay, proof. Well, remember that this lambda omega d are a minimum over a bunch of things. So in order to show that a minimum is bounded, that a minimum is bounded by something, I just have to give you examples. What is the example? This sine of pi over 2x. Why is this the good example? That's kind of important. This is the good example because this is the first eigenvalue of the interval, the first eigenfunction of the interval. So if my measures are converging to the uniform measure of the interval, this is probably the most efficient enemy, like the sharpest boundary I can get. And what happens when I pick this phi this? Well, I have this limit. The phi's are constant. These weights converge to the uniform measure in minus 1, 1 cross 2 in the y variable. I don't care about the y variable. So I converge to this. This is great. So now I don't owe you anything anymore. I've shown you that the eigenfunction is radial. I've shown you that the eigenvalue is at most d. And now I have to tell you more things about the potential. I'm only going to ask for one more thing about the potential, but it's a really weird thing. So I'm going to ask you that the flow lines of the gradient flow by your potential look like this. This is, again, a qualitative picture. Like anything that qualitatively looks like this is enough for a counterexample. The thing that I need is that for everyone, so remember, I want to show that the maximum and the minimum are right at the bottom. So what I want is that everyone that's not at the bottom, so everyone that's like here, here, or here, when I flow with the flow lines of this gradient U-twiddle, I end up flowing, and if you follow the trajectories, right into the middle or extremely close to the middle of this little interval where most of my mass is. So that's my condition, that for everyone that's starting in the areas where I don't want a maximum, and I flow, I end up essentially in the middle. And the moral of this is that convex flows, like gradient flows by convex functions, are not particularly nice. They can be quite nasty, especially when you can play with a lot of scale. And this is everything we need about the potential. Now we have all of the ingredients to build a counterexample. So first lemma that you have to believe me about is regularity. These functions psi d are uniformly bounded and equicontinuous. This seems innocent. It's not. If you look at the PDE that they satisfy, they have coefficients that grow faster and faster, that grow to infinity. This is a singular PDE, but there's something that is called like dimension independent or dimension free Harnack inequalities, which were proven by Li Yao in the elliptic case and then by Wang in the parabolic case. And if you use them carefully enough, you get uniform boundedness for the psi. More the idea is that if you have uniform Harnack, you have uniform continuity. You have to be a bit careful about it, but that's about it. And that's enough. The reason why that's super powerful is because every time I extract like a weak limit in any sense, I can transform it into a strong C0 limit by Arzelà-Ascoli. So right now I'm just gonna like extract convergent subsequences of the psi-ds, and they will have to converge strongly automatically. So the first claim is that in minus 1, 1 cross 2, in this core where most of the mass is concentrating, the functions psi-d converge at least in an infinity to sine of pi x. So the one that I showed you before, and I think it's pi over 2. I forgot a pi over 2. But sine of pi over 2x. Why is that? Well, the measures nu d converge to this uniform measure. The lowest Laplace eigenfunction of this measure is pi squared over 4. And there's only one function that witnesses it, which is sine of x. We know that our eigenfunctions will have to eventually witness it. You extract a convergent subsequence, you play some Fatou tricks, and just by uniqueness of the lowest eigenfunction of sine of x, you get that when the psi-ds have a limit, it has to be the limit of this, because the limits will converge to minimizer of the what is it, of the Dirichlet energy, of the Dirichlet-Rayleigh quotient in that little strip. So out of nowhere, suddenly, we know the value on this strip, on this little line. That's kind of magic. And it follows like from the coercivity from the spectral gap of the interval. And now the second one, which is like kind of where like all of the magic goes, is that if you had any subsequential C0 limit of this psi-disk, then this subsequential limit has to be constant in those flow lines that I built before. And this is again like by just playing with the PDE a little bit. So you look at the PDE that the psi-disk satisfy. It's the gradient of the potential, which is d minus 1 times grad u twiddle times grad minus Laplace psi d equals lambda d psi d, but I just brought it to the other side. Now, let me rewrite this like this. You have nabla u twiddle times nabla psi is equal to this thing, which goes to 0. Now, extract any weak limit of the psi d's. It will be a weak solution of nabla u twiddle times nabla psi d is equal to 0. The only weak limits to this equation, this is a transport equation, the weak limits of this equation are the things that are constant on the flow lines defined by u twiddle. So that's it. We built this limit of the psi d's. For now, it's a subsequential limit, but then you show that every subsequential limit has to be the same. So you follow the lines of the gradient flow, and then what you get is this. So the value right at the slit is a sine of x. It goes from -1 to 1. And to see what's happening outside, you flow back with the gradient lines. Everywhere where we did not want a maximum is being pushed by these flow lines right into the middle of the strip, where psi is essentially 0. And there's some points where psi is at least -1 or 1, which are just sort of contained here. What this shows is that the maximum cannot be in the areas where we did not want the maximum, and therefore you have to go back and remember that we came from this like cylindrical coordinates kind of problem, and that this lower line, where the maximum and minimum could be, corresponds to r equals to 0, and r equals to 0 is smack inside of the interior of the material. Okay, a bit of a recap of what we did. So we talked about how essentially every dimension-free resulting convex analysis has a log-concave analog and their equivalent. We've shown that a stable version of the convex hotspots conjecture, this like pancake type version, would imply the log-concave hotspots conjecture. And then the question is, and then we saw that the log-concave version of the conjecture is false. And then at this point, the question you have to ask yourself is, well, maybe hotspots is different from every other conjecture I've seen before, or every other question I've seen before in this flavor of convex analysis. And actually, like the hotspots conjecture is still true. But no, the hotspots conjecture behaves like basically everything else. And what you can prove is that for all large dimensions, there exists a convex set for which this eigenfunction does not attain the maximum. What do you do morally? You get this example that I've drawn now, where you have a potential that behaves in a really weird way, and then you build a barrel construction, the barrel construction that I presented before, on top of it. So you found a problematic example with a potential, and you have a way to simulate potential. Well, you use the simulating tool on top of the problematic example. There are slightly easier ways of doing it, and the paper takes a slightly different route, but this is the main idea, and you can actually also make this approach. So that's everything I wanted to say. Thank you very much.
We can all thank the speaker for the great talk. So do we have some questions? Don't hesitate to just go for it if you have any questions.
I'll start with one. So you mentioned the logarithmic bound in KLS in the KLS conjecture or theorem. Do you know if the recent improvements on the Burdzy slicing argument,
I've been asking around. The paper doesn't say so, and my understanding after asking people around is that they kill it up to logs still. They like you can't go for free from slicing to KLS without using logs, but like The paper itself, I was looking at the paper by Kartek and Lehek, and I didn't see them claiming anything about KLS, and I asked people what was the deal, and that was the answer I got.
Okay. Okay.
But I'm not like, that's definitely like far from my field of expertise. So yeah.
Well, I have a question. Thank you for the great talk. First of all, it's a wonderful result. Do you have an idea starting from which dimension the hotspot is false?
No, I'm talking to people that know a lot more numerics than I do, and we're trying to see if we can reproduce this example. When I was trying to follow my own proof, I didn't even get to the end, and I already needed some lower bounds that were in the 4 digits. So I realized that like following my own proof was going to be not illuminating at all. The proof is effective. If you wanted to take the time, you would get to a really big number out of it. But right now we're trying to see if we can like construct, following the spirit of the proof, like a specific low-dimensional example with a number that like we're not embarrassed to say out loud. So yeah, no, I don't have. And the other thing is like I don't like this proof. Like there's like all of these other like problems which fail after a certain dimension, and we know why. Like there's like one canonical example. I don't know if we're ever going to see that in a hotspot. Like it feels like it at some point it's just like not true, but we don't know why. Like we don't have like the one canonical. Like this whole proof is very non-canonical. It's definitely not giving us the right reason why hotspot is false.
Questions? So in that case, we can thank the speaker again. Thank you for the great talk. So we reconvene next week with a talk by Benjamin Florentin, who will tell us about the Steklov spectral inverse problem in the conformal class. In the meantime, have a lovely week and bye-bye.
Thanks a lot, Jaume, for the talk.
Thanks a lot.
I was wondering from a heuristic point of view, this sort of failure in high dimension, is this related to this sort of heuristic that in high dimension convex sets are quote unquote not that convex and have a lot of their mass concentrated at the boundary?
Yeah. So I couldn't. The thing, let me share my screen for a second. Actually, for this, like my iPad. Share. So I couldn't present the proof is the paper is not very long, but it uses a lot of different ideas, which is okay.
Yeah, I mean, I had tried looking at it, and I decided that I would wait on hearing the talk first, and then.
So the talk is missing, like the talk and the paper have less overlap than I would like, because I mean the actual paper. What I'm showing here, I figured out quite a bit, like almost a year before the whole proof. And the paper, like it has so many little things that I haven't figured out how to give a 1 hour talk on that proof that is not just like throwing stuff at the audience in a way that cannot be understood. But so there's one very important idea in the paper, which is very much in this direction, which is exactly when you look at these barrels. How do you call it? Most of the mass of the barrels is near the boundary. And then you actually we do something that's like a little bit more subtle, which is that we consider this to be size roughly square root d, and then we repeat the same variable, so 1 minus v of d over d, and most of the mass is still at square root of d over the approximately 1 over square root of d neighborhood of the boundary. So most of the mass is here. And what ends up happening when you look at the PDE that the radial guy satisfies, so you now get this guy, you write it in polar coordinates. These are over square root of this, say, and this is the omega naught. Most of the mass is here. So in other words, something really funny happens, which is that the value of the PDE here on the black region does not depend on the value of the PDE on the blue region. But the value of the PDE on the blue region does depend on the value on the black region. And you end up with this like really weird situation where you have that your phi, and let's say that this is actually 1, and this is 0. And I'm omitting that the change of variables is a little bit more subtle than just taking radial coordinates, but we forget about that. And you end up getting something like psi of x comma 1, where 1 means here the top, is the psi naught omega v of x. So right at the top, you see the effective problem because the thickness, the amount of math that's on the little slice, is proportional to like the e to the minus v, which is essentially what we already used in the talk. And outside, what is a PDE that like only sees outside but doesn't see inside? A PDE that like only sees like one side of the domain. That it's a heat equation. Like that's the number one PDE that like that has like this asymmetry that like these points see this but not vice versa. So when you write everything correctly, what you end up seeing is minus partial t equals Laplace. See, a minus this minus right now is just important because I'm like backwards heat equation.
Yeah. It's backwards. It's backwards.
Plus the lambda omega v. So you end up with this PDE. And this is a very high dimensional phenomenon. So when you're in very high dimensions, it turns out that the Laplace equation becomes a heat equation precisely because of this, because like convex sets are very non-convex. Most of the mass is outside. So you only see the outside, as opposed to like, if you think of it like in terms of Brownian motions, the Brownian motions are always moving outside. They're not just randomly walking. They're going where most of the mass is.
Yeah, exactly. I mean, it's transience. It's transience of the Brownian motion, right?
You can see it from the but it's way stronger than just like qualitative transience. It's like you're leaving. You're like exactly. So you use that, and in very high dimensions, this transience becomes essentially deterministic, and that's why you end up with a heat equation. Like the distance to the origin becomes essentially deterministic in very high dimensions by like concentration of law of large numbers. Each coordinate is independent.
Yes.
But that means that the distance to the origin is deterministic. So you get a heat equation because there's one variable, which is the radius, in which you're now deterministic. And then you have to use all of these. And when you go through all, so all of this is what like the part that I couldn't explain, which is what happens when you use the barrel. Like how do you like upgrade from like log-concave examples to convex examples? And there you need to use very much what you're saying, that convex heads are not convex. But morally, like but you only see exactly. And this is it. It's a 1 hour talk, which is annoying because I don't get to like. I mean, there's so many little things that you have to pick, and I had to throw away all of this because like if I say this for 5 minutes, I'm gonna confuse people more than if I just completely omit it.
Jaume,
hi!
Hi,
I wanted to meet you at some point. Hi.
Yes, likewise, yes. Wonderful
by the way,
talk,
I have some news for you that you're gonna get excited about.
Really?
Your square of E,
right,
is sharp.
That was exactly the question I was going to ask you right now.
It's sharp. We know the exact value in every dimension now.
I was going to ask you that exact question. Yeah.
So it's not for convex sets, but like simply connected sets and so on. Probably, hopefully, in a couple of weeks it will be in archive. But it's we have like
beautiful.
We have like a sequence of counterexamples from below, and we're able to match them in every dimension. And asymptotically, your result is sharp.
That's amazing. That's cool. I was just going to ask you if you had for convex sets, if you had some kind of estimate on the constant hotspots constant.
No, convex sets are really hard. I have no idea.
Yeah.
Also, if you go carefully through the proof, it's also like, I mean, what we know, so something that you can do if you go carefully through our proof is to show that. So if let me share my screen. You're on Mauricio. So I define like following your like you and Steinerberger. I define, let me say, SD conv is the maximum over omega RD convex max x in omega phi omega max x in the boundary phi omega. So following your definition, what you can show out of the paper is that the lim inf of SD conv is bigger than 1. So not only there's examples, but like the examples are uniformly lower bounded in the dimension. I mean, a priori, something like something that I thought and I thought still could be true, but in the end, no, is that maybe the conjecture becomes more and more true again as t goes to infinity.
I see.
And there was an initial approach that didn't work to find a counterexample, which would not have shown this. But if you go through the current counterexample and you follow everything, you actually get these as well. So there's it makes sense to talk in some sense about the limiting hotspots constant for convex sets in the same way that you do in your paper.
Right. Yeah.
What kind of property would have made the conjecture become true again? As I mean, I
mean
would have
like
thought
less
that,
false, like less false. It could
yeah,
be impossible.
sure. But I would have thought that large dimensions make everything false, right?
Maybe so. That I originally so in the proof as it works right now, I have to use these bigger and bigger. How do you call it? Bigger and bigger convex sets, like radii as the dimension increases. Originally, what I was trying to do in the proof strategy was to use smaller and smaller radii as the proof increases, as the d increases, which is kind of more natural. And there you would have had that in the example. Something that's quite annoying about hotspot is that it doesn't behave well under products, doesn't behave well under adding dimensions. It should, something by the way that we know now is that this constant, like the SD, not for convex, but like in general, for the bigger than or equal than 2, since we know it exactly, we know that it's monotonically decreasing. But we know it from the example, but monotonicity, there's no reason to believe it's increasing. So actually adding dimensions for, if you don't have convexity, adding dimensions makes the conjecture more true in a certain sense. It converges to square root of E. It starts like at 3 point something. But there are like nasty numbers with Bessel functions and so on. But you do asymptotics and they go to square root of E.
Interesting. It's funny because at one point we thought that in high dimension the square root should have been 1.
No, it's true. It's true.
I thought like maybe in high dimension everything is like a ball or something. I don't know.
Yeah, exactly. That's what it was very weird. Like we were trying. So there's an old paper by Nadirashvili and Jeris where they just drop there's this other counterexample. And then we were like, let's see in that counterexample what's happening. Let's compute everything very carefully. And we found the square root of E and we're like, wow, this is and then we started pulling and we got every dimension. But it was like your square root of E was the one that made us realize that we were onto something.
Okay, interesting. Oh, that's wonderful. Yeah, this is a beautiful result. That's awesome.